Okay, we're back. This is the last chapter. Oops, let me turn on my light. There we go. This is the last. I didn't really do any good. This is the last chapter we're going to cover. Yay! That's very exciting. And it is on chapter 10.2. It's on limits and motion. Okay, so we're actually going to learn a little bit of physics here. Not very much physics, but a little. So but we're going to use some of the things we've talked about with limits and derivatives and stuff to talk about them. Now, first of all, dang it, hold on, I don't know why this thing does it. Okay, draw on that monitor. Okay, now we're good. Okay, so if I have displacement, and this is going to be in meters, versus time in seconds, and I have this. So we go up to some time and displacement value. Well, this graph looks like, oh, and we know the slope on this graph equals the velocity. And the slope would be change in distance over change in time. So let's write it d over t equals v. And I think the book uses rate. So let's use rate. There we go. Rate. And so distance equals rate times time. If I was driving 50 miles at 10 miles per hour, it would take me 5 hours, right? The hours would cancel, we'd get miles, 10 times that is 50, blah, blah, blah. Okay, so here's the basic equation for distance equals rate times time that we've learned many, many times. And the slope of the graph is the rate, is the velocity. And when I look at this straight line graph, I notice that in a straight line, the slope doesn't change. It's supposed to be a straight line. Pretend it is. Humor me. So the slope is constant, so the velocity is constant. So if I were to draw a velocity versus time graph, and here's 1, 2, 3, 4. Okay, 1, 2, 3, 4. What happens for these 4 seconds? Well, it looks like the slope is staying constant, so I'm not speeding up and I'm not slowing down. I'm staying the same. And so a constant velocity would look like this. It's supposed to be a flat line. So this will be my constant velocity because it's not changing. The slope is staying constant. The speed is staying constant. Okay? And if I look at my equation, distance equals rate times time, and the rate is the velocity, that, oh, wait a minute, VC, that's this distance, and T, that's from 0 to 4. So length times width, this kind of looks like the area of a rectangle, doesn't it? Oh, look at that. It looks like on a velocity versus time graph, area equals distance. And more specifically, this velocity is really the derivative of distance. If this is s of x, s of t, then velocity is really s prime of t. because we know that the slope of the line, the instantaneous slope, is the same as the velocity. So I know that really when I'm talking about velocity, I'm talking about the derivative of the displacement function. So this is the derivative of displacement to the velocity. And the area on my derivative function gives me what? Oh, the area right here gave me distance, right? The area on the derivative of the displacement function gets me back to the original displacement function. So when I find the area on this graph, it's going to tell me how far I've traveled at that time t. Well, that's interesting. So what if I had something like velocity and time, and I had a function that was like that. And I want to know at time t, if this was my velocity function, how far did I travel when I hit this point at t equals something, t equals 4? I don't know. How do I find the distance traveled if I know the velocity function, but I don't know the distance function? Well, just like we said before, I could go and calculate the area underneath here, and I could figure out what the displacement is. So on here, the area under the curve equals the displacement. Does the area under the curve only equal displacement? Only if it's velocity versus time. That's the only time that the area under the curve will give us a displacement, is if we're using a velocity versus time graph. And the reason why that is the case is the velocity. So this is s of t. The velocity is s prime of t. And when we calculate the area under the displacement curve, it takes us back to when we find the area under the velocity curve, it takes us back to the displacement. Okay, so we got to be very specific about that. So let's say we have function. So this is water flow measured in, gallons per hour. And this is time in hours. So, and I don't know what we call this. We'll call this water flow, W of T. But notice the units, gallons per hour. This is similar to meters per second or miles per hour. The water flow function is the derivative of the gallons. I don't know how to put that. This is like the, prime. It's like the derivative of the gallons function, the derivative of the numerator of that slope function. But anyways, so if I go up to here and I get to 3 hours, 100 gallons per hour, and I want to compute how many gallons have flowed out of there. Well, if I want to know, if I want to go from gallons per hour this looks like a slope thing to me, just like meters per second. It was like a slope thing. So if I want to figure this out, then one way I can get from gallons per hour to my gallons function is I can calculate the area under my gallon prime. And this thing is my derivative. So if I want to find the gallons, I can find the area underneath the curve. And fortunately, this looks like a triangle. And I can do area is 1/2 base times height. So 1/2 times 3 times 100. Half times 100 is 50 times 3, 150 gallons. That's how we would calculate the amount of gallons that flowed when this shows the water flow in gallons per hour. Okay? We want to get from gallons per hour to gallons. We can't just multiply by gallons. We could if the function looked like this. And this was gallons per hour, and this is hours. Right? And this is, so that's, that would be 100 gallons per hour, and this was 3 hours, right? If it's just a constant thing where the gallons per hour don't change, it's just a fire hose with water coming out at a constant rate, then the area under the curve would be 100 gallons per hour times 3 hours. Oops. Those would cancel and we'd get 300. But this shows the flow rate started out at 0, and then the amount of water that was coming out was increasing. The rate of water flow was getting bigger and bigger and bigger and bigger and bigger. And to figure out how many gallons, we'd compute the area underneath the curve. Okay, so we'd get 150 gallons over here. So that's an example of how we would use the area on the rate thing to get back to the original function and find the amount. But frequently, we're going to have a function that looks like, let's see if I can draw a decent curve. Oh, not so bad. Okay, so something that looks like that. And if I want to know what's the area under the curve, well, come on now, that's not a very nice thing to have to ask me to calculate, because it's not a triangle, it's not a rectangle, it's some goofy curve. I don't even know what it is. And even if I knew what it was, that's going to be hard. But if you recall, for our triangle, oh no, and that's going to be confusing. Let's pause for a minute here. Okay. So if I have something like f of x equals 2x. So that function is nice and convenient. It looks like a line with a slope of 2, right? This is y equals mx plus b. And so when I want to know, so this is f of x, and this is x, and we want to go to 4. We want to know what's the area under the curve. The way we would write this mathematically is we would say the area under the curve is equal to the integral. This is the integral sign of f of x dx. And I'm integrating from 0 all the way to 4. So I'm getting the area under the curve from x equals 0 to x equals 4. And if I write that in my fancy calculus speak here, that would be f of x is 2x. Okay? This is how we would do it in calculus, but that doesn't mean very much to you right now. But what this means, when we do an integral, we're finding the area under the curve. And the way we would compute this is 1/2 base times height. We might write it as the integral like this, but we're going to use geometry to figure it out. And so if f of x equals 2x, excuse me, and this has an x coordinate of 4, let's see, f of 4 would be 2 times 4, which would be 8. So the y coordinate is 8. So 1/2 base times height. 4 times 8 is 32, times 1/2, 16. So that would be our area underneath it. Okay, so triangles we like. Those are okay. But what if we have f of x equals x plus 3? So now this looks still like y equals mx plus b to me. A slope of 1, a y-intercept of 3. So 1, 2, 3, and a slope of 1. I got to do it a little lower. There we go. So there's 1. And we're doing it. I want to know what's the area under the curve from 1 to 4 of f of x. I want to know when I go from 1 over here to 4, what's the area underneath this bad boy? What's the area underneath that? Well, it's a trapezoid. And let's see, this would be, let's figure out, f of 1 would be 1 plus 3, it would be 4. Okay, so here is the point 1, 4. F of 4 would be 4 plus 3, right? I'm plugging x into here. 4 plus 3 equals 7. So over here, this would be the point 4, 7. So maybe you remember that this is a trapezoid. And the equation for the area of the trapezoid equals 1/2 times the sum of the bases. Here's B1 and here's B2 times the height. And the height would be this distance. So you could plug this into the formula and do that. I'm betting not very many of you remember that. So instead, I'm going to treat this like a rectangle and a square. This distance is 3. The y-coordinate here is 4, so that distance is 4. And let's see, this base of the triangle is 3. And if that's 4 and that's 7, then this has to be 3 as well. So my integral from 1 to 4 of f of x, meaning what's the area underneath f of x between 1 and 4? That's going to be the area of the rectangle plus the area of the triangle. So that's going to be the area of the rectangle is 4 times 3, and the area of the triangle is 1/2 base times height. So 12 plus 3 times 3 is 9, times 1/2 is 4.5, 16.5. So that's the area underneath this trapezoidal thing here. Okay, you could just use this if you remembered that. If you didn't, always break it up to triangles and rectangles, and that makes it so much easier. Now, let's say we have, don't save, integral from 0 to 4 of 4x plus 3 dx. 4x plus 3, that's mx plus b, y-intercept of 3, a slope of 4, and we're going from 0 to 4. So I need to figure out if f of x equals 4x plus 3, f of 0 will be 4 times 0 plus 3, which will give me 3. F of 4, will be 4 times 4 plus 3. 16 plus 3 is 19. And so this point is at the point 0, 3. We kind of knew that. This point is at the point 4, 19. Now we can go and use some geometry. And again, if you want to use the trapezoid area equation, right on. I don't. This height is 3. This width is 4. This base of the triangle is 4. This is 19. If this is 3 and the height is 19, this would be 19 minus 3. This piece of the triangle would be 16. Okay, so the area under my curve of 4x plus 3, the dx tells me what variable I'm using here. I'm using x. Is the area of the rectangle plus the area of the triangle. So that's going to be 4 times 3, 1/2 base times height. So that's 12 plus, let's see, that's 2 times, half times 4 is 2. 2 times 16 is 32. So this comes out to be 44. Ta-da! And I think that's the end. Let me look at the book. Ugh. Cannot believe how heavy they make these books. But it looks like that's the end of it, as far as I can tell. Yeah. No, I think we'll do some Riemann sums. Do I want to do that? I don't think I want to do that. So I think we're just going to end it right there. Come to the homework session and we can talk about more of these problems so you can see how they work. And there you go. Make sure you do the homework, come and ask questions, and we'll see you later. See you at office hours. Everyone's coming, right? Good. Okay, bye.